So, welcome back. In the last few lectures, I discussed about Beer-Lambert's law, and Beer-Lambert's law is probably one of the very important laws that we have, and it is used in lots of atomic absorption spectroscopy for measuring the concentrations of metals. In organic chemistry, it is used to measure lots of absorption by the different compounds that are there. The solution phase, same way, it is to know the concentration of absorbing species. So any absorbing species that is present in the any matrix that can be used, whether it is a solid usually is not used in the kind of Beer-Lambert's law. We usually in the liquid and gas phase. So these two are used. So I told that the equations were very simple. Okay. So for the gas phase, for the liquid phase, we used to use epsilon Cl. For absorption, we used to use here our attenuation. We used to use like ln I0 upon I, and then here this is not represented in this form. It is reported as usually ABS, absorption coefficient, and B attenuation. So this is the two things that are very important that we have to remember. Remember here, this absorbance is actually unitless, but when we report this absorption, our absorption coefficient and attenuation coefficient, here the unit becomes 10 to the power minus 6 meter inverse. So this is the only difference, but this is a very big difference between the two that we have. Now we will see some of the applications of Beer-Lambert's law, and at the same time we are moving now towards the sort of optical properties that we had a very specific lecture on this one, a specific chapter that we have to cover. And in extinction, so there are two ways that is there. Actually it is extinction, and generally the extinction is like when we say that extinction is sum of absorption plus scattering. So when you add both the process, then it is called scattering. So when we say that light is extinct or light attenuate, it doesn't really mean that it has to be because of the absorption. It could be because of the absorption, it could be because of the scattering, or it could be because of both. So when we say attenuation means both the process are considered. So this is actually, for example, attenuation of light along an axis resulting from scattering and or absorption, or scattering or absorption. So this is actually definition of extinction. And then particles, extinction is dependent upon the chemical composition of the particles as well as particle size, shape, orientation and number. So if you have very high number, the extinction coefficient will be high. The particle size, there is a very specific size. If the particle size is less than that, there will be no scattering, actually forward scattering or backward scattering. There are two types of scattering, forward and backward, and absorption is of course dependent on the number concentration, and then shape is also very important, and orientation. So we will come this one in the coming lectures, but just to give you an idea here that what is actually. And light is very important, that is also dependent upon the polarization and then frequency or the wavelength of the incident beam. So extinction is also dependent on the polarization. So this is one of the reasons that usually we use monochromatic light. So if you use monochromatic light, then polarization and other things are not complicated. So this is one of the reasons we usually use monochromatic light. Okay. The very first application is actually like aerosol optical depth. And one more thing actually, when you measure this absorption in the liquid phase, there is another nomenclature for this one. They are also called as optical density. Okay. Although you remember, whenever we refer to the density, density usually refers to something like divided by mass or volume. Okay. Usually generally defined by the volume, so divided by the volume, but here optical density is actually refers to the measure of absorbance itself, or some of the parameters they usually report this concentration epsilon. This is also sometimes mistaken as optical density. So you have to be very careful that what is reported in the literature, and whether it is absorbance is given, whether it is transmittance is given, and whether the units of say molar absorptivity and path length and concentration, they have actually similar or the way they have been defined. So this is very important whenever you are doing the calculation, and I am sure that there will be almost like every exams, as I said earlier also, there will be some questions on this one. So please be careful in calculating these numbers, it is very important for you. Then what is aerosol optical depth? So this is very important. There are very important things here. If you just remember, this is aerosol, so this means this optical depth that is related to the aerosols. Okay. And now what is the depth? When we say depth generally means something below. If you are measuring some height below something, then it is called depth. If you are measuring up, then perpendicular to the surface, then usually it is called height. But if you are measuring something below, then it is called depth. So how the name came in the depth? Because what is happening here, we generally assume that solar radiation, sun is actually emitting radiation from the sun, and our atmosphere is beneath the solar radiation, and we are coming here. So this is why the depth, by depth it is decrease, it's below, sun is if you just take sun at the upward and you start measuring from the sun, then it will actually we will call it depth. Something you can just correlate with this one. And with something optical we say, so when we say optical means something that is related here, some of the optical properties like incident radiation that is coming here and outgoing radiation, and thus how much actually aerosols is there. We will come to this later, just in next slide. And if you see that how much aerosols, how much light is extinct because of the presence of the aerosol. So there are two things that will be coming into the picture, that the integral of the light extinction by aerosols within an atmospheric column. So this is important, that you have to have atmospheric column. It's a aerosol optical property is an actually columnar property. And if you remember in the very first lecture, when I taught about aerosols, I taught that how the aerosols are reported in the atmosphere, or in the textbook, or how will you report, what will be the concentration. So usually they are reported either in microgram per cubic meter, okay, in generally, because you have aerosols means particulate matter, so this will have something mass, and then it is suspended in the air, so it will have volume. So one way to report this concentration of aerosol is aerosol optical aerosol concentration in microgram per cubic meter. The other way to remove tell the aerosols that the concentration of aerosols is aerosol optical depth. Now this is very standard, that if you have a high concentration, if the concentration, you can say that if you measure, and you can just see that whether the concentration is high or low, and you can say the concentration, whether it is polluted or not polluted. So we use those terminology, whether it is polluted or not polluted. We use the threshold level of concentration. Above that concentration we say that it is polluted, below that we say it is not polluted or it is there. And but here what is actually there, the other way, so it is actually kind of, you don't here the column is not there, there is no column actually. So it is, column is not there here is just a volume of air. In the volume, how much mass of the particulate is there, that's all, it doesn't say. Then other way, of course I talked about here, since it is given in the mass, you can always convert it into number concentration. So this is also very important, this is also number times, sometimes number concentration is used in the literature, that how much concentration is there. So if you have high number of particles, the concentration is generally high, but it depends actually, okay, because the mass will be actually number into density. So there are two things, mass will be depending on the number as well as actually density. So if you have a very high number of particles which have less density, then for example ultra fine aerosols, they are very abundant, but they don't contribute much to the mass because the concentration is very low, that's density is very low. Whereas dust aerosols, they are bigger in size, okay, and their number is less, so they contribute more to the mass, and therefore if you see the particle size distribution, you will see mass is more dominated by the larger mode particles compared to the, so this size is also related here, okay. Now here, so this is not a columnar property, it is a property that is directly measured per unit. You take 1 meter cube of air and you try to measure that how much concentration is there. We will see, and we will come into the next lecture, that how, and next few lectures, that when we do aerosol sampling and aerosol measurement, then we will come to that one lecture later. But here what is happening, as you said, this, so it depends on the what is the columnar height, how much height is there actually, or how much depth is there, and how much aerosols are present in this one. So this actually, if you have more number of particles, there will be more extinction, right? One thing. And otherwise, if you have more aerosols which are actually giving more like extinction, such as more absorbing or more scattering, that way also it can be there. So it is actually a columnar. So if you just in the previous slides, if you remember, this A is equals to epsilon CL. I will use these equations very often. So now I hope that you are very familiar. So absorption will be higher if your either concentration is higher or here the path length is higher. So if the air is traveling to a longer distances, then the path length, the optical depth will be higher. And this you can correlate with the phenomena during the daytime when the sun is on the top of us, our head, it will be traveling less. So that time the scattering is less. Whereas during the evening hours, 5 to 6 hours, when sun is actually inclined to the earth's surface, and but not 90 degree, less than 90 degrees, say 5 to 10 degrees centigrade, the radiation has to travel a larger distance. So at that time the scattering is more. Okay, this is one of the concepts that you remember here. So this is how it is related. And then aerosol, remember this is a columnar property, number one. Number two, it is related to the size distribution. So aerosol size distribution is very important. Here the concentration, reporting the concentration, it is not mandatory for you or for us to report the size distribution, what size of particles are dominating or not, but here actually size distribution is very important to report. And generally higher or larger optical depth is related to a thicker layer or cloud. So this means more extinction. So when we have high AOD, this is actually very kind of so if you have a thicker layer, so this means you have more pollution. One thing, or you could have a cloud. So clouds are very scattering, they scatter the solar radiations much. So this means, and we discussed that, we will come to that one equation, that if you have the extinction is sum of the scattering and absorption. So if it is more scattering, this means extinction will be more. So this is how it is used to define this one. So thicker, larger AOD means it could be actually a more pollution or more polluted atmosphere. So if you have to compare two atmospheres which having less AOD and one having high AOD, you will be talking about in the terms of pollution, or you can also talk about the in terms of the cloud, whether it is a cloudy atmosphere or not. Okay. So optical depth is calculated from the spectral extinction of direct beam radiation at each wavelength based on the Beer-Lambert's-Berger law. So you remember this law, we have been discussing this one, and this law is used. Now there are few more terms that here you have to use each wavelength, okay, and then spectral extinction of direct beam radiation, because our solar radiation contains several wavelengths, right from what you call gamma rays to the longer wave, Hertzian wave, and because of that one you have to consider all the wavelengths, but we will come to that when we will narrow down. We see that for us the absorption in the UV, visible and IR regions becomes more important compared to other regions, because other regions we don't talk about the aerosols and other things. And attenuation could be due to Rayleigh scattering or absorption by the ozone. Now this is very important. I talked about that the scattering and absorption could be either due to the particulate matter or the gaseous species that are present. So it could be either attenuation, could be either because of the scattering or absorption, scattering and absorption, or it could be because of the scattering or absorption, both. So absorption by ozone molecules, gaseous pollutants and gaseous pollutants is estimated and removed. So when you attenuation due to Rayleigh scattering, when you have to calculate, when AOD we have to calculate, then absorption by the ozone molecules and other gaseous pollutants that are there, they are estimated and they have to be removed to isolate aerosol optical depth. So aerosol optical depth, as the name suggests, it's because of the aerosol itself. So because in the atmosphere we know that there are apart from the aerosol particles or the aerosols or particles, gaseous species also scatter and absorb the solar radiation. So when you have to measure, because the radiation, if you are totally measuring, it is not doing everything actually. So the absorption or scattering is not because of the particulate matter, it's because of the particulate matter as well as gaseous pollutants. So you have to remove the absorption and scattering because of the gaseous pollutants in order to get the AOD values, and this is what is happening here. So suppose this is the the atmospheric column that we have, and the thickness of the column is okay. Sometimes this thickness is also represented as dz. So this column is supposed L, thickness is L, and now you assume that there are all the particles, whatever number of particles are there, whether are less or less, they are contributing to the beta extinction, or extinction coefficient is actually contributing to the extinction coefficient, which means this is actually either because of the absorption or because of the scattering, okay, both. So this is beta extinction is actually this means you have to put it here absorption coefficient and scattering coefficient both. So basically B absorption and B scat, and if you just multiply these two, and then beta extinction will have a unit of 10 to the power minus 6 meter inverse, and then thickness is actually unit is actually like unit is in meter. So if you just multiply this one, the unit will become, they will become unitless, and this is actually you are having a terms that is called optical depth. So this is actually unitless, and sometimes, not sometimes, it is mostly called aerosol optical depth, not aerosols, aerosol optical depth. Okay. So aerosol optical depth is nothing but the extinction coefficient, which is the sum of the absorption and scattering coefficient and the path length through which the light is traveling through. So now if you assume that at any particular height z, this intensity of the radiation is I0, and then here again Iz, then there will be a relation that Iz can be written as I0 exponentially minus tau. So this is very important equation, and this tells that the light is attenuated depending on the optical depth. So if the optical depth is very high, the light will be attenuating faster, or if the optical depth is more high, you have more extinction, and when you have more extinction means you have probably more particles that are there in the atmosphere, so they will be contributing to the extinction coefficient. Okay, yeah. So coming back to again this question, just remember this question. Sometimes this aerosol optical depth is also, it is a measure of extinction caused by scattering and absorption of aerosols. So I have been telling this one. So I0 is equals to, you can write I upon I0, you can write, we wrote that I, or you can write Iz, or Iz is equals to I0 exponentially minus tau. Okay, and tau was actually B extinction into x or dz, so whatever you are writing. Okay, and if you are writing B extinction into dz, then you have to integrate, z is right from 0 to whatever the height you are taking, and then you integrate this, so B extinction will be function of z, then you can calculate tau. So this is actually very important parameter to define, and this again, this actually, because this extinction is dependent on the wavelength, so this means this parameter is dependent on the wavelength. So aerosol optical, this means the aerosol optical depth is also dependent on the wavelength. And that's why this wavelength dependence, when you see this one, we will discuss that how the aerosol optical depth is related to the wavelength, then we can calculate this one. So just to give again extinction coefficient result, I have been telling this one, tells the sum of the extinction from gases and particles, each of which in turn can be divided into extinction due to absorption and scattering. So B extinction is because of the gas and then particles, and then B extinction can be either B absorption by or B scattering, and now scattering by the absorption by the gaseous molecules, they will follow the Beer's law. Okay, because the concentration they will be dependent on the concentration itself, whereas scattering will be following Rayleigh scattering. Okay, and when so there are actually, by the gaseous molecule we will have Rayleigh scattering, and when we are talking about the scattering by the particles, it is called Mie scattering. So just remember, gas scattering by the gaseous molecule is called Rayleigh scattering, whereas scattering by the particles are called actually Mie scattering. So this Mie scattering, which is also sometimes, see number, the way it is written, also written because of the BSP is written because scattering due to the particles also, or B sometimes BSCAT, or sometimes it is written as BSCAAT double T, and then usually if you just calculate B absorption upon B extinction, this is actually less than 10%. Okay, so this means you have more of scattering aerosols than absorbing one. Okay, and this means this is 10% or 0.1, and this means the particle is mostly scattering. Okay, so more of cooling aerosol. Imagine a situation that the atmosphere was made of absorbing aerosols. What would have been the case? They would have been absorbing more solar radiation, and when they would have been absorbing more solar radiation, the Earth's temperature would have been increasing. So we have more global warming in that sense. And this terminology we will discuss. This is called single scattering albedo. SSA, which is similar to terms like albedo. Okay. So in the ultimate limit to the visibility in very clean atmosphere is the Rayleigh scattering, because when you have ultimate limits means you have very high visibility, and when you have very high visibility, this means you have very less aerosols, or almost you have no aerosols. Okay, so ultimate limit to the visibility will be a very clean atmosphere, and at that time, because you don't have clean atmosphere, you have almost like a clean atmosphere. At that time, the scattering will be dominated by the gaseous molecule, and then if this is dominated by the gaseous molecule, it is called Rayleigh scattering. But usually, my scattering usually dominates when we are talking in the troposphere, because you have more of particulate things that are there. The range of scattering coefficient is 10 to the power minus 5, or it is also written 10 to the power minus 5 can be written as 10 to the power minus 6 into 10 into 10 to the power minus 6, and then meter inverse. So this can be written as capital 10 mega meter inverse, and when you have 10 to the power minus 3 means 10 to the power minus 3 means 3 has to become here, and then so it is like, a scattering coefficient ranges from 10 to 1000 10 to the power minus 6 meter inverse. Yeah, this is again what is the actually kind of filtration of photons, and then you do this kind of equations that are there actually, and Beer-Boger's law. You see here how this is actually one of the very important equations to calculate either actually extinction efficiency or monodispersed aerosols, number of monodispersed aerosols. Okay, that how many monodispersed aerosols are present in the system. So this is the principle that how this is actually used to measure the nephelometer. Okay. Okay, so you have particles here, and you have a light source. So light source will be condensing on the lens, and then lens will be collecting the all the lights here, and then lights can be actually in a way it will be divided in such a way that it is passing through this aperture of the aerosol kind of column or kind of things that we have here, and when it is passing through this one, it can be actually these aerosols can be actually calculated that how many aerosols are there. In this, I think this needs a separate discussion, and because if I start this discussion, this will need another 5 to 10 minutes. So I will start this discussion in the next lecture. So I will be stopping here, and then we will see this one, that how it can be calculated. So this is again in this lecture I discussed about the importance of the scattering and absorption coefficient, and I introduced the concept of aerosol optical depth. We discussed scattering and absorption coefficient, and how to calculate these things, how they are actually related to aerosol optical depth. In the next lecture, what we are going to do, we will be doing some kind of calculation on the scattering and absorption coefficient, and then finally the aerosol optical depth. And in the next lecture, I will also discuss about the single scattering albedo and other things. So with this, I will stop here, and till then, I hope that you will be enjoying and reading some more about these courses that I have taught. So thank you so much.